Hello again, everybody, and welcome back. This is episode 3, which surprises me, of my video about the Jeti circular coupling, particularly with respect to a Bernreiter, or indeed any other vectored thrust tube. And in this video, I'm going to show you 3 things. First of all, a minor modification to my original program, which now gives perfectly circular movement. So the radius remains at 100 all the way around. Secondly, Lawrence Bernreiter, manufacturer of the Bernreiter vectored thrust tubes, has sent me a little video showing me his program for it. So I'll show you how to do that, and we can use this visualization tool to show you the effect of it. And finally, Dave McQueenie, who wrote this visualization tool that you're seeing on the transmitter screen, just for fun wrote a Lua script to do this, and he sent it to me, so I'll show you how it does it absolutely perfectly, as you might expect. However, I don't think that Dave will be releasing the Lua app to public release, because we tend to share the same feeling that little homemade Lua apps, even when they're written by professional software people, maybe not a good idea to put on a primary flight control that can affect the path of the aircraft. So I don't think his app for the vectored thrust will ever become available. It was done just for fun. First things first, here is my original program, which I demonstrated in episode 1, and I have tweaked the demixing numbers to get it to work pretty much perfectly, at least at the edges. Now, I went to a lot of trouble in episode 1 to show you the trigonometry of how I arrived at the numbers for the demixing curve, which is great, but that sort of assumes that only one curve is going to be doing the demixing. And of course, once you push both sticks, then the numbers start multiplying together and brought the circle in a little bit. So I've simply done some empirical tweaking of the numbers on the curve until we get this perfect mix. So whereas before, when I moved this around, the radius of the circle would drop a little bit down to about, what was it, 95, 96 at some points. It should now stay at 100 all the way around, pretty much. As before, the red dot signifies where the sticks are and where the nozzle of the vectored thrust would go to if you didn't modify it. So for instance, up here, if you didn't modify it, the nozzle would follow the sticks up to that corner there, but we want it to go around in a circle, because going beyond that circle, Bernreiter says extreme forces may result and could do some, or extreme forces will result and may do some damage. Okay, so we'll show you it's going around in a circle. Watch the radius here, stay at 100. So off we go, there's full yaw. Now I start pitch, yaw, yaw, pitch. So if you look at the actual visualization, you can see it's going round in a circle, and that VR number at the bottom is staying at 100. So we've done it. We've got truly circular movement. In reality, it'll be shifting by fractions of a point, but does that matter? It's rounding to 100. That's nice. So what did I do differently? If we go to functions, not functions assignment, I want the function curves. And it's here in the 2 decrease curves. There's just a slight change to the numbers that I used, and I'll show you what they are. So it's still 29 at the edge. Then the next point is modified to 15, 6, 2. Then you're at 0, 2, 6, and 15, and 29 again. And it's the same for the VTY decrease. So if you want to, just change the curves to those numbers, and the result is lovely circular motion. There we go. Okay, let's hop to another model now. And the next model, I'm going to show you how Lawrence Bernreiter programs it and what the result is. And what he did was, we have functions assignment. You can see we've got pitch and yaw, as we did in mine, but there isn't the pitch or yaw decreasing functions. Don't need them. Okay? What we'll do is we go to Advanced Properties, Logical Switches, and we create two logical switches, a pitch one and a yaw one. Let's have a look at that. Control 1 in the pitch is the pitch stick, set to linear. Okay. Control 2 again is the pitch stick, but with a slight change. We've switched on reverse so that it goes in the opposite direction to the first one we've done. Yeah. So if I pull the stick back towards me, you can see that the first control sticks come back, but in the second control the stick's gone forward, it thinks. Set to linear, set as OR. And the reason for doing that is that the output number doesn't go negative. That one switches on when we push the stick that way. That one switches on when we pull the stick that way. The OR switch is happy to accept either one switched on, but it means that it only takes the positive number. Yeah? Never goes negative. Okay. And just do exactly the same for the yaw. Use your yaw stick as the input, set to linear. Down here, control number 2 is the yaw stick, but with reverse switched on. Okay, so again, it does the same thing. Condition is OR, and full left, full right, the number always goes positive. Okay, now you create a couple of mixers. You create a pitch mixer where it's pitch to pitch. The master value, I've used -29 because that will leave you with 100 minus 29 equals 71. And 71 is the length of the hypotenuse of the right angle triangle formed by 100% yaw and 100% pitch. And that will give you the curve point. Okie doke. If you're not sure about that and you want to understand better, have a look at episode 2. Otherwise, just accept it. The switch is Logic Switch 2, which was the Yaw Logic Switch. Remember, we've created two logic switches, one with pitch, one with yaw. So in the pitch-to-pitch free mix, you put in the Yaw Logic Switch. And what effectively that does is start demixing the yaw value from the pitch value, gives you the curve. Okay, doke. And then you create another free mix, in effect the same thing, but this time it's yaw to yaw at -29%, and this time the logic switch is the pitch logic switch. Okay, no need to program up any curves. Rightio. And then that is your job of programming done. So let's have a look at the result. Once again, use Dave McQueenie's visualizer. So once again, the red shows where the stick is. The blue shows where the output is actually going for the servos. And again, if I push the sticks to the corners, red shows where the sticks are and where the servos and thrust vector tube would go if we weren't using this method of programming. Blue shows where the yaw tube's actually going to go. Okay, let's have a look at what shape that makes. Can you see that? What we're getting is an octagon, an 8-sided polygon. Let's build it up a bit before it... Okay. Now, you can see if I hold on full yaw and half pitch, the radius drops from 100 to as low as 93. There, get now full pitch, if I start reducing yaw, the radius can drop to 93. So what it's doing is straight lining between the 8 points. So there's 1 point, midpoint, 2, 3, 4. So it's going in a straight line rather than round the curve. And at the lowest ebb, as it were, or the biggest difference between the straight line and the curve is 7%. So you're losing a little bit of possible travel there at the edges. Okay, it's less time to program it, Probably no more easy, because if you just follow my videos, well, if you just sit there and follow the numbers, done. But there's less time there. And if you remember, in my program, if you have partial movement of one and then you move the other, it'll start to curve away. What Lawrence Bernreiter's program does is it goes off also, but in a straight line rather than a curve. So where that's a solid straight line in the diagonal, my program starts off vertically and then curves off and ends up pretty much at the same point. So they've both got similar sort of behavior that way. However, if you prefer this version of the program, it's going to have small gaps because of the straight lining it's taking, but it's pretty much doing the job, isn't it? And it certainly stops you, pardon me, from overdriving the servo at any point, which was one of the things Lawrence Bernreiter is trying to avoid you doing. So that's that one. Let's carry on and have a quick look at the little Lua app written by Dave McQueenie and how it behaves. Vector Mix Lua app. Here we go. And let's watch it. We'll see it go round and round in the circle as I move the yaw and the pitch sticks, and the radius will be locked at 100. So here we go. See that lovely circular movement with a radius locked at 100. Crucially, what does it do at partial? Does it do what we really want it to do? If I push the yaw out to here. Now, as I push on pitch, in my program, it starts off straight but then curves away off until it meets the circle. In Lawrence Bernreiter's, it goes off at the diagonal straight away till it meets the curve. The ideal behavior you want is that it goes straight up until it meets the curve, and only then does it start following the curve round. Otherwise, if you're trying to hold on a constant amount of yaw to do something, you don't want that changing just because you've added in a bit of pitch as well. So here we go. Does it go up straight? I'll move it out here. Or does it curve away? Look at that. Goes up straight. How lovely. And then it only curves once it meets the curve limit. So, as you might expect from writing proper software, this is the perfect program. But as I said at the start, Dave and I tend to share the same feeling that it's not a wise idea to let a Lua script loose on primary flight controls. So Dave wrote this just for interest and a nice little challenge. And say if you follow the program I've shown you from Lawrence Bernreiter, you get very close to it. If you follow my program, there's a bit more programming work to do, but you get pretty much perfect circular motion anyway. So no need to bring in the possible risks of a Lua script on your flight controls. And but it shows it can be done. So there you go. There's 3 different ways, 2 of them publicly available to you, to get the circular or close to circular coupling of vector thrust tube, or indeed any other item that you need to do. Have fun with that, and goodbye for now.